So first of all, I would like to say thanks for the organizers for inviting me. It's a great place. I took a walk this morning, very beautiful. So I'm going to talk about subgraph-based networks. And when I say networks here, I mean graph neural networks, and not graphs in a different word. OK, so let me start with just acknowledging the students that made most of this work. So Beatrice, Fabrizio, and Derek led the works that we are going to talk about today. They really did a wonderful job. And the talk is going to be based on those two papers. The first was presented at iClear this year. And the second one is going to be presented at the end of this month at NeurIPS. OK, so let's start. First of all, maybe a quick introduction to why we want to learn on graphs, why this is interesting. Well, you're a good audience for that, but of course you know that graphs can model a lot of interesting real-life phenomena. So one good example is molecules, which are can be easily modeled by graphs by using the nodes as atoms and the edges as molecular bonds. But the truth is that there are many other cases in which learning on graphs is relevant. So just a few would be social network analysis, visual question answering, trying to understand visual scenes in images. People even use graph neural networks in order to solve combinatorial optimization problems. So GNNs have become a very hot topic in machine learning these days. And I would like to start with the setup we are going to consider in this talk. We are going to consider a supervised learning setup in which we have a bunch of graphs and labels. Each graph consists of an adjacency matrix and node features, which are just vectors in RD. And our goal is to find a model F that can take this graph as input and output the correct label. And of course, we would like it to be able to generalize to unseen graphs. And I think the fundamental question in this field is, what is a good GNN? How to model the GNN in a good way? And this is what we're going to talk about today. So just a bit of previous work. By far, the most popular approach these days to learn on graphs is by using models or architectures called message passing neural networks. And those neural networks perform local message passing using parametric functions. So at each layer, they take as input for a specific node the set of neighboring features, and they aggregate it in a permutation invariant way, and then they update the node feature. If we want a global feature for the whole graph, we can sum over all those features and get the final feature. So this is a great model from many perspectives. It is very scalable. It's easy to understand. But the problem is that it has a fundamental problem. And this brings us to the topic of expressive power. So let me explain what is expressive power for graph neural networks. So let's assume that I get two non-isomorphic graphs, G1 and G2. The question is whether a message passing neural network or a GNN in general can separate them. And separation means that we can take a model with a specific set of weights that outputs different values for the two graphs. This seems like a trivial thing for MLPs, for instance, or for images even. But for GNNs, it turns out that this is not the case. So there is a limitation to the expressive power of message passing neural networks. And this is an example. We will see some in more detail in a few minutes. But here we can see the graph representation of two molecules Those are different molecules, but a message passing neural network will output exactly the same output on those two molecules, which means that if we have a classification problem, we cannot really classify them to different classes. This is a huge problem. The underlying reason for this is the close connection between message passing neural networks and an algorithm called color refinement. So color refinement is a very efficient heuristic for graph isomorphism. And the idea is to take a graph and to color it in an iterative fashion until you reach a steady state. Then you get a graph representation that you can compare to the representation of the other graph. Let's see how it goes. So let's say that this is the initial graph. And we have the same features at the beginning on the nodes. So after one iteration, we color each node by the current color and the multiset of the colors of its neighbors. We use a multiset because we don't really have a notion of order between those neighbors. We do that again and again until we reach a steady state. And at that point, we just compute the histogram of the different colors. And this is the graph representation. You can think about it as a multiset of local node descriptors or something of that sort. And two incredibly interesting papers from 3 years ago have shown that message passing neural networks and color refinement have exactly the same separation power. And I think this shouldn't be a surprise because the update equation of the message passing neural networks is basically very similar to what the color refinement algorithm does. By the way, I didn't say it, but please interrupt, ask questions. I'm OK with not finishing all my slides and having a nice discussion. Yeah.
So do you always have a fixed point for?
Do I always have?
A fixed point. So for example, you always find because you say you iterate.
Yeah. Yeah. So you will get to a stable. Like it's pretty easy to show that you will get to a stable coloring.
You don't have like multiple like.
No. Because each iteration is a refinement of the previous one. This is like the main thing. Yeah.
Linking the two, you started talking about this DL test with the same feature, right?
Right.
In GNNs, you can have different feature per nodes. Does the issue still persist?
Yeah, sure. So in cases in which we have categoric features to the nodes, which is often the case for atoms, for example, we can show exactly the same problems. In some cases, people use GNNs in order to process continuous data, like point clouds, for instance. And in that case, separation is, in most cases, not a problem because the node features are sampled from some continuous distribution. But message passing neural networks have other difficulties in that case. But we are going to limit ourselves to discrete features at the beginning. OK, so the color refinement algorithm is also called the first WL test. WL stands for Weisfeller-Lehmann. You probably heard about this test. This is a fundamental work from the 1960s. And there are generalizations of this Weisfeller-Lehmann test called K-Weisfeller-Lehmann. Each one of them is stronger than the previous one and requires more computational complexity. And this is something that we're going to mention in this talk today as well. So let's see an example for why MPNNs have limited expressivity in some more details. So we have this graph, the original graph, and if we apply message passing to or WL or message passing to it, we will get the following coloring and the following histogram of colors. On the other hand, this is another graph. And obviously, this graph is not isomorphic to the previous one, but we get exactly the same histogram of colors. So this should provide some motivation to why message passing neural networks are so limited. I should say that this is not just a single example. For example, you cannot separate between any d-regular graphs with the same number of nodes. And those kind of things really come up in practice. OK, so why do we care about expressivity? We have talked about the first point here, which is we cannot assign different labels to different graphs. And this is obviously a problem. But the second issue here is something that people talk about less, but I think it is important. This is the issue of being able to compute meaningful features for the graphs. So for example, in many cases, we know that some substructures have huge importance on the functionality of the underlying graph, if it's a molecule, or for example, on some other features of the underlying graph. Think about rings in molecules or cliques in social networks. But it turns out that message passing neural networks cannot detect those substructures. So if your underlying function is actually a function of those substructures, you will have a problem. OK, and I think since those two papers in 2019, there is a surge, probably more than 100 papers on, maybe more, on expressive GNNs, which means coming up with new architectures that are provably more expressive than message passing neural networks. And usually, this will involve some trade-off between computational complexity and the expressive power. So the first approach is called KGNNs or KIGNs. And in general, that means that we have neural networks that are capable of implementing the KWL test. And they have provably more expressive power. But again, instead of using like limited time complexity, they will use high-order tensors and high-order operations. And this turns out not to be practical for learning. It's a nice model for theoretical study, and we will use it. But this is not something that people actually use. So for example, no one implemented KIGN for K bigger than 2, I think. OK, so another prominent approach is to promote differentiation between the graphs by adding some random features. And those random features can be sampled from continuous distributions. They can be sampled from discrete distributions. And it's not too hard to kind of realize that it is pretty easy to separate graphs with those random features. But the problem will be in the actual results or generalization, which will be problematic. So again, this is a nice theoretical idea, but it doesn't work in practice. I can say that one of my current projects is trying to find a way to make this work. We're still not sure how to do it, but I think it's an interesting problem. The last kind of family of methods is methods that use domain knowledge. So let's say that I want to work on molecules, and I'm an expert in this field. I can find some special structures that are important, like rings, like other stuff, and I can model them in my architecture. So for example, one simple way to do it is to count those substructures and have some node features that will indicate how many of those substructures are incident to each node. And these kind of methods work pretty nicely. They provide a boost in expressivity and in generalization. But in many cases, we don't have this domain knowledge. So this brings me to the goal of this talk today, which is we are going to look for GNNs which have three main properties. We would like them to be domain agnostic, meaning that they can work on any field without having an expert in this field. We would like them to be as efficient as we can. And we would like them to be expressive. And in many perspectives, this is the main goal of this whole field of expressive GNNs. This is what people are trying to achieve. So the main observation that will lead us today is that we can gain more expressive power by representing a graph as a set of subgraphs. For example, here we have the original graph on the left side, and on the right side we have a set of edge-deleted subgraphs, which means that in each subgraph I delete a single edge. And let's try to understand why this gives us more expressive power. So we go back to those two graphs that we saw before. So we have the subgraph types on the left side. Oh, sorry. And this is the stable coloring that we get from WL, and this is a histogram of the histograms of those subgraphs. So this becomes our new representation of the graph. So this is the histogram for this graph, this is for this one, and this for this one. The numbers here indicate the number of times each subgraph occurs in the original graph. On the other hand, we do the same for the other graph, and you can clearly see that those histograms are not similar. So we have a clear separation of those two graphs. So this is like the main motivation that we had. And this gives us the following idea. In order to process graphs, what we are going to do with neural networks, we are going to first map a graph into a bag of subgraphs. When I say bag, I mean multiset. And then we are going to process this bag with a neural network. And this really brings up two main questions or challenges. The first one is, what is a suitable architecture for processing sets of subgraphs? The second one is, which subgraph selection policies are useful, are interesting, are computationally efficient, and so on. So we'll talk about those two questions now. Maybe if you have questions, yeah. Yeah, great questions. We will see that we use both ideas. So the idea in this paper is to create a framework and not to specify one single method that will work. And we will see both. Yeah, any other? OK. OK, so let's start from architecture. And I think this is probably the most interesting question here. We're going to use a notion called equivariance in order to come up with a good architecture. And the next few slides are going to explain what is equivariance and why it will help us. So first, we will start with a group of transformations that act on our inputs. And a good example here would be to think about images and to think about translations. And we are going to call this group a symmetry group of the input if those transformations are not really relevant to what we are trying to obtain or what we're trying to compute from those graphs or from those images. So if a cat is found on the left corner or on the upper corner in an image, it doesn't matter for us. This is still a cat. And we would like our model to be invariant to those kind of transformations. For graphs, we have a similar thing, right? We would like to be invariant to the order of the nodes, right? This is something that is arbitrary, in most cases, at least. And we would like to be invariant to that. So a function is called equivariant, which is a generalization of invariance, if it commutes with the group operation, which means that if I apply first the translation, for example, and then the function, it's exactly the same as applying the function and then the translation. And usually people use those commutative diagrams in order to exemplify what's going on. So a common principle in the last, I would say, 30 years is to model your architectures or your parametric models in general to be equivariant in case your target function is equivariant. So we know that for a lot of functions on graphs, the function is invariant or equivariant to permutations. And it makes sense to reduce the size of the hypothesis class to functions that obey to this rule. And a nice way to do that is by concatenating simple equivariant functions. So that there are lots of theoretical and practical benefits for doing so. So we'll just list 3. You get significantly less parameters. In many cases, you can actually count the number of parameters. If you're interested in that, let me know. It's kind of a nice application of representation theory to deep learning. You get a better generalization because you restrict your class of functions, and you get lower computational complexity. And I think by far the prototypical example. Yeah.
Sorry, just one question. Two slides before, you said that the class of equivariant networks are included in the set of MPNNs. So is it really true? I mean, we have an equivariant network which is not an MPN?
So what I'm trying to say here, this diagram represents the closure of this space of networks. So we know that MLPs can approximate any continuous function on a compact domain. This is the celebrated universal approximation theorem, but equivariant networks cannot, because they cannot approximate functions that are not equivariant. So there is a strict gap between those two. Okay. Okay, so by far the most famous example for that kind of construction is convolutional neural networks, where the inputs are images. The symmetry group, we can think about many kinds of symmetry groups, but the most popular thing to do is to think about translations. And then the basic layers are convolutions, which are just translation equivariant functions, which are linear. And the resulting architecture is a CNN. And OK, it's a good time to go to our case, because we want an architecture for sets of subgraphs. So we know what is the input, don't really know what is the symmetry group, what basic layers should we use, and what is the resulting architecture. And this is what we're going to do now. So here we have the original graph. And some illustration of its bag of edge-deleted subgraphs. And this is the tensor representation. So in each one of those matrices, we see the adjacency matrix of their corresponding subgraph. And what we would like to do now is to try to understand what are the symmetries of this structure. In other words, what kind of transformations we can apply to this, which will not change the essence of the underlying object. So one thing we can always do is to permute the nodes of the subgraphs, right? We don't really care about the order of those nodes. And we can do this for each one of those subgraphs. By the way, they are aligned, so we can use the same permutation for each one of them. And this will be interesting in a minute. Another thing we have is the set symmetries. So we don't really care about the order of the subgraphs, right? So if we look generally on that, we see that we have an internal graph symmetry and an external set symmetry. And in the deep learning literature, there are ways to handle both of them. Many people work on the graph symmetries, specifically each GNN is permutation equivariant. And many people worked on set symmetries. If you have heard of PointNet or deep sets, two pretty famous architectures that deal with this case. And the question here is how to combine the knowledge that we have to each one of those symmetries to a joint symmetry. So I should say that a way to combine those symmetries, and we will see this in a minute, is to use a direct product of those groups. So essentially, we say that the permutations on the nodes and the permutations on the subgraphs are independent of each other. And luckily for us, we have a paper from 2020 that deals with exactly this case. So we assume that we have a set of input objects. And each one of those objects has some symmetry H. And we assume that the symmetry group of this whole input is the direct product between them. And we give a characterization to linear equivariant layers in that case. So I remind you, linear equivariant layers are the basic building blocks that we use for convnets, for example. And this is the parallel of convolutions for this structure. And the idea is pretty simple. The output for the ith item would be some equivariant function applied to this function, and another equivariant function applied to the summation of all other elements. Any questions about that? So this is basically a theorem in linear algebra. It's pretty easy to show. If you're interested in that, let me know. We can go over that. OK, so taking inspiration from this characterization of simple equivariant layers, we propose the following basic layer for sets of subgraphs. So we start from this set of subgraphs. We apply one thing we do is we compute this summation or aggregation of all those subgraphs. You can really replace it with anything you want, like max or some more sophisticated stuff, which is permutation invariant. We apply one type of GNN, or not one type, but one instance of GNN to each subgraph independently. We then apply a different GNN. You can think about a message passing neural network in that case, to the aggregation of all those graphs. And then you combine the results. And this is the analog of the characterization that we saw when we replaced the H-equivariant layers that we had in the characterization with GNNs. And the whole network looks like that. We will have this input of list of subgraphs, several concatenated equivariant layers, and then we will have some pooling operation and a deep set encoder. So this concludes the part of the architecture. And one can show that this architecture is indeed equivariant to both the node permutations and the set permutations, or in more mathematical terms, to the action of the direct product of the group. So we turn now to which subgraph selection policies we can use. This was not the main focus of the paper, but still we suggested 4 different policies The first one is edge deleted, as we saw, in which for each subgraph we delete a single edge. We also have node deleted subgraphs in which we delete a single node at each time. And we have the local version in which we extract the ego network around each node. And this comes with a parameter which says what is the size of this ego network. And in that case, we can actually identify the root node or not identify it. And this gives additional expressive power. But those are pre-designed subgraph selection policies that we use. For very large graphs, using edge-deleted or node-deleted policies is going to be a problem because we have many of those. So one thing we tried is to sample in a stochastic way subgraphs. We tried several percentages, like 5% and 20 and 50%. And the main benefits we get from that is that we can process larger graphs, and it improves the running time significantly. The problem is that we might represent each graph in a single graph in a different way. So there is some kind of extra knowledge that the network should be able to understand in order to map those two graphs into the same place. In our experiments, we show that this works quite well. So first of all, we come up with a new Weisfeld-Lehmann variant. We call it DSS-WL, that kind of represents the process of coloring the subgraphs and then counting the histograms of those subgraphs. And we show that this is strictly more expressive than the standard 1WL test. And we also have several other nice theoretical properties. For example, we show that edge deletion is stronger than node deletion in some cases. Maybe it makes sense to you. I can offer some intuition if you want to talk about it later. And we also show that if you use stronger graph encoders, so let's say that instead of message passing neural networks, I will use some stronger encoder, then we will get higher expressive power. So this is monotone in this kind of expressive power of the base graph encoder that we use. From the experimental point of view, I will show results on a data set called Zinc. This is a molecular property prediction data set in which you take a graph as input. The graph represents a molecule. We are interested in drug-like molecules in that case. And the output is some property of this molecule. Here we use the log P. And what we can see here is that DSS-GNN obtains, which is the main model that we discussed, obtains very close results to the state of the art, which is CIN. And CIN is a paper that models molecules directly. So I think this is a nice result that we have an agnostic method because we didn't put any domain knowledge. This is all pretty general into the architecture, and we still get very similar results to specialized methods. OK, any questions until now? This is kind of the end of the first paper, and now we can talk about the second one. So it's a good time for some questions. Yeah.
I have a question regarding the subgraphs. So basically what you're doing is that you're taking a framework and putting on different versions of the initial graph. How would that compare to just doing some data augmentation with these subgraphs with the classical analysis or something?
So I would say data augmentation is kind of similar to our case with stochastic sampling, with the number of samples being 1. So we generalize that, and we show that we perform better. But I think that those two ideas kind of come from the same place. If you, instead of using just one subgraph, you use many subgraphs, then you get more expressive power and better results.
On the type of data that you have, because is Ego Plus, for instance, working really that well for a different experimental?
Yeah. So this is a great question.
This seems quite,
Yeah. It's pretty large.
Doesn't seem very interesting. Yes.
We found that the ego policies work particularly well for molecules. I'm not sure if I have a good explanation for that. Maybe we should ask an expert. But I think this is a limitation of this method. The fact that there are some predefined policies and you need to choose one of them. And indeed, one direction that we have started working on is learning the selection policy. This is a problematic thing because learning a discrete policy is going to be not straightforward. We are going to use some reinforcement learning techniques in order to do that. But definitely, I think that this is the way forward for this little field of subgraph GNNs. Yeah.
Can you discriminate the regular graphs, which are normally added?
Yeah, with edge deletion policies, you can. So if you're interested in that, you can take a look in our paper. We have like a very nice characterization with respect to strongly regular graphs.
So general question, I'm not super familiar with the literature. What about the features? Don't they play any role in making subgraphs and in guarantees? Like,
so when we extract those subgraphs, we take the features with the nodes that are left. So they are naturally part of this framework. Is that the question?
yeah, I kind of didn't get the message about like if the features play any role in all these decisions that you have to make about what subgraph to select, etc.
Oh, whether certain features could be indicative for certain subgraph selection policies.
And if they play any role also in the expressive power, of the neural network that you're constructing.
So our whole analysis here is takes into account discrete node features. So everything I mentioned applies to that case as well. And yeah.
Yeah, a question about edge removal, the edge removal policy.
Yeah.
Do you need to remove all the edges, or are you subsampling a set of edges that you remove in any
Okay, so
stochastic, is it a stochastic algorithm?
So for theoretical analysis, we remove all the edges. We have experiments both on the stochastic sampling scheme and on the full subgraph selection policies. And we show that using the full approach is better in most cases, but you get significantly better results than standard MPNNs, even when you use the stochastic approach. But this is definitely another limitation. I would say it is related to what was mentioned here just a second ago. You would like to learn small subgraph selection policies. This would be like the best case. Yeah. Yeah.
Is there space to use like attention layers in this kind of framework?
Yes. And this is also something that we have started working on. Yeah. So I imagine that this will not give more expressive power, but will probably give better results experimentally, which is also important. Okay. So this paper was published, I think, half a year ago, something like that. And when it was published, we saw that there are actually I think I have like 5 papers here, but there are like 10 papers now that follow this same methodology of looking on subgraphs, applying MPNNs to those subgraphs, and then aggregating the information in some way. And all of those papers show that those networks are better than standard message passing. And what we try to think about at that point in time is whether there is some pattern here, whether we can find some way to compare all of those methods with some framework that will generalize them all. And this is what we did in the second paper that is going to be presented at NeurIPS in a few weeks. So in order to kind of understand what we are doing here, we will take a slight detour and talk about invariant graph networks. So those are based on a paper from 2019. And the idea here is that you start from an n by n adjacency matrix representation of your graph. And then you use linear equivariant layers. But those layers are able to map you to high-order tensors as well. So we can think about an adjacency matrix as a 2-tensor, but you can think about a 3-tensor that represents this graph. It just represents all interactions between 3 nodes. And for k-order, the same. And people have shown that k-IGNs are equivalent to the KWL, which is kind of nice because we have 2 seemingly unrelated hierarchies, but one of neural architectures and one on expressive power of some combinatorial algorithm. But it turns out that those 2 hierarchies are exactly related. And another thing that we focused on is on the so-called node-based policies. So what are node-based policies? Those are policies in which each subgraph is related to a specific node in the graph. So in node deletion, it's pretty obvious, right? Each subgraph is related to the node that we took out. In ego networks, it's also quite obvious because each subgraph is extracted from a specific node. And I can say that the most widely used policies in all the papers that we saw before are node-based. So those node-based policies can be represented as a 3-tensor in the following way. We just stack those subgraphs in this cubed tensor. So we have 1 dimension for the subgraphs, and the other 2 dimensions represent the node interactions. So this is really a stack of those adjacency matrices. And one nice thing that we have in that case is that we can order those subgraphs according to the order of the nodes, right? This is something that we can definitely do. While this seems like a technical thing, it actually shows that we can model our symmetry group in a different way. So I would like to remind you that in the previous paper, we had independent permutations for the subgraphs and for the nodes. But in our new case, we can use exactly the same permutation. That means that the symmetry group can be chosen to be just Sn, the symmetry group on n elements, and not a product of 2 groups. Informally, this shows the following nice outcome. So Sn is informally smaller than the product of those of Sn with itself, and the function space behaves in an inverse way. So if you're less constrained, you're more powerful. And a direct application of that shows that subgraph GNNs are limited by 3WL. And this is because we can simulate all subgraph GNNs with 3 IGNs. So again, 3 IGNs are bounded by 3WL expressive power. 3 IGNs can implement all of the different subgraph selection policies and all of the layers that we discussed. And so if you can separate a graph with subgraph GNN, you can separate it with 3WL as well. So this answers an open question on the upper bound of those methods, because people didn't realize that this is still bounded. Another thing that we show in this paper is that we can come up with a nice layer space for subgraph GNNs. So here we concentrate on the subgraph to nodes plane in this cubed tensor. And we realize that this has the same symmetry as 2 IGNs, because those two permutations are the same permutation. And then we take inspiration from the characterization of linear layers in that case, and come up with a very nice and natural, I think, space of layers. I will skip the exact thing here, because I would like to finish. But just to let you know, this is an illustration, a graphical illustration of the previous layers that people have suggested. This is a new layer that we suggest, and this is like the full layer space. So there is a lot of opportunity here to discover new things that will probably work better. And from the experimental point of view, we actually close the gap to CIN even more. We have some nice results on the generalization ability, but I will not talk about it now. I would like to conclude. So first of all, I'm not sure how many of you are working on this or know this GNN expressivity thing. I think it's a great field, and it really affects the results of neural networks, of graph neural networks. So if you're interested in that and you would like to know more, come talk with me. I'm happy to discuss. Another take-home message is the subgraph GNNs seems to me like a prominent direction in this search for expressive and still kind of efficient methods. And maybe something even more general would be that symmetry analysis is a very nice way to come up with new architectures for items that or inputs that you would like to process with neural networks. And the main meta algorithm here is to first understand the symmetries of your data, what you don't care in your data, then come up with simple equivariant functions, and then use them to build invariant or equivariant networks. And finally, in most cases, you would like to do some kind of analysis of the expressive power in order to make sure that you didn't lose a lot of expressive power, because what we do here is restrict the hypothesis class. OK, some advertisement. I'm beginning my position at the Technion at October 2023, looking for students and for postdocs. So if you're interested, let me know and tell your friends. And that's it.